Walter, good morning.
Good morning, Professor. How are you?
Fine, thank you. Buenos días.
Buenos días in Spanish.
And are you ready to make your presentation?
Yes,
Okay.
we can. Firstly, we can make a proof. For example, if can I share my presentation?
Yes, please. Please do
Okay,
it.
okay. Let me 1 minute, please. Could you check if my presentation is correct?
We are seeing the presentation screen, not the full screen. Maybe you have the are you already doing the presentation with in full screen mode? It's not in full screen mode. We are seeing exactly your screen. So we can see the contents on the left and the next slide on the right. If you
maybe maybe check this one. For example,
the last one on the right. I think it's the last one on the right.
okay, this one.
Yes.
Now you can check my screen.
Let me check on the YouTube channel because your presentation will be streamed live. Yeah, but it's not 100% okay.
Yes, I am use the presentations dot damianopenpair.it.
Oh, but you have two screens or just one screen?
Two screens, but nevertheless, I don't know if you can see my all screen, or if you prefer, I open my presentation in PowerPoint and share it.
Yes, but I think you have two screens. Maybe you have two screens and we are seeing just one screen. We would like that you share the other screen, maybe.
So
If you
tell
have
me what I have to do.
in the screen sharing, in
Okay,
the screen sharing button, you have to.
let me leave the sharing now.
Yes.
I go back to my room. Here
Okay.
I find some bottom of sharing.
Yes, for the button that you use to share, there's
Okay,
a one that you can ask for the which screen.
okay, let me see. Uh, we have full screen, just a window.
Full screen,
Okay, full,
or just a window, or you can use just a window and choose the one with the
okay,
presentation.
okay. And for example, share, and now
The window.
it's correct. There is my presentation.
I think we can read it, so I think it's better to do it this way. Yes, we can see our presentation. It's not fully using all the screen, but it's good enough. But I thought this was, yeah.
So I can start now.
Yes, yes, please.
Okay, let me. Okay, can I start so in this moment?
Yes, please. Welcome, Walter Fuertes, and please start your presentation.
Okay. Good morning with everyone. Thank you for being here. My name is Walter Fortes. I'm going to show you my presentation entitled A Model Implementation to Detect Hate Speech Associated with Gender Violence by Natural Language Processing and Machine Learning. I work at the Department of Computer Science at the Universidad de las Fuerzas Armadas ESPE in San Joaquín, Ecuador. I have divided my presentation in 4 points. The motivation and problem statement, the research design, with the data construction and training, classification models, system architecture, web prototype, the results, and the conclusion of future work sections. Okay, so what is the motivation and problem statement? This research is motivated by the growing problem of hate speech against women on social media, the rapid expansion of online platforms and user anonymity have increased the spread of discriminatory, offensive, and stereotypical messages that undermine women's dignity, safety, and participation in digital spaces. Although many existing models detect general toxicity, only a few specifically address gender-based hate speech. At the same time, increasing legal and ethical requirements demand automated accuracy and scalable content moderation solutions. Therefore, this research proposes an hybrid approach designed to improve the detection of hate speech, specifically targeting women. In other words, our goal is to develop a model for detecting and preventing hate speech against women on social media, combining natural language processing and machine learning in order to contribute to safer, more inclusive, and more respectful digital environments through the use of artificial intelligence. Okay, so we can start explaining the data construction of ETL processes. This slide summarizes the ETL process used to build the data set for our study. As you can see, there are four phases. Extraction. First, we collect the data from multiple Kaggle data sets, resulting in approximately 2.87 million raw records. The second phase is transformation. Next, we clean the data by removing duplicate entries and null values, ensuring linguistic consistency across the corpus. The next phase is labeling. We then applied a 0.5 Boolean threshold to convert the original scores into binary labels, preparing the data sets for the classification tasks. And the last phase is loading. We finally consolidated the cleaning and labeled data into curated corpus of 440K samples, which was used for training and evaluating our machine learning models. At the end, this ETL pipeline ensure the quality, consistency, and reliability of the data sets throughout the research process. Okay, let me explain the classification models. As you can see in the screen in the left side, this slide illustrates how the BERT model identifies a hate speech message. First, the sentences is tokenized, converting the text into tokens that the model can process. Next, BERT performs directional contextual analysis, understanding the meaning of each word based on its context and its relationship with other words. Based on this analysis, the model detects characteristics such as gender stereotypes, limitations of social roles, and gender discrimination. Finally, it classifies the message as hate speech, specifically as gender-based discrimination and sexist stereotyping. In other words, this approach enables the model to classify messages based on their semantic context rather than relying solely in the presence of office words. In the right hand, you can see the classification model using random forests. This illustrates how the random forest classifier works. First, the input text is converted into numerical representation using the TF-IDF technique. The resulting feature vector is then processing by multiple decision trees, each independently producing classification. Finally, the individual predictions are combining through majority voting to generate the final prediction. This ensemble approach improves robustness, reduces overfitting, and increases the overall accuracy of the model. To the end, in other words, the final decision is not made by a single tree, but by the collective consensus of the entire forest. Okay, we join these previous models in this model combination, okay, and uses Gemini Flash filter. This slide presents our proposed hybrid model. First, both BERT and random forest independently analyze the same input text. Their prediction probabilities are then combined using a weighted fusion strategy, assigning 60% weight to BERT and 40% to random forest, reflecting BERT's strong semantics understanding. The class with the highest combined probability becomes the final prediction. If the message is classified as hate speech, a second validation stage is targeted using Gemini Flash 1.5, which verifies whether the content specifically is woman. This additional filtering step improves both the accuracy and the specificity of gender-based hate speech detection. In trust, by combining traditional machine learning with a large language model, our approach leverages the strengths of both techniques to achieve more reliable classification. Now we can see the system architecture. Okay. Mm, Now we can see the system architecture. This figure presents the overall system architecture proposed uh, in our research for detecting hate speech against women in social media. The process begins when the user submits a comment through the web application. The comment is sent to the server via a REST API implemented with flags following model view controller architecture platform. On the server, the text preprocessing analyzed by the hybrid model composed by Bear and Random Forest, whose prediction probabilities are combined to produce an initial classification. If the message is identified as potential hate speech, a second validation stage is performed using Gemini Flash, which specifically verifies whether the content target women reducing false positives. In addition, Google Translate enables multilingual processing, while Firestone stores both the comments and the classification results. Um, then we can find the next slide, the web prototype. Okay. Here we can show the prototype development to validate our proposed approach. The application was implemented using Flask and Python following the model visual controller architectural pattern. We separate the user interface, business logic, and data management. The client communicates with the server through a REST API that sends every post to the speech detection and service. The data is stored in Firestone, a cloud-based NoSQL database that provides scalability and flexibility for managing social media network. Now we can go to the results sections because the time. Um, this slide presents the performance comparison of the evaluated model. The bar chart on the left shows that the combined model achieved the highest accuracy, reaching approximately 96%, outperforming both the standalone BERT and random forest models. The table in the right hand provides a more detailed evaluation using precision, recall, and FU score for both classes. Across all metrics, the training model delivered the best performance, achieving the 97% precision up to 96% recall and FO score of 0.96%. These results indicate combining BERT and random forest provides a better balance between correctly identifying hate speech and reducing misclassification, resulting in more robust classifier than either one alone. The um, next slide, uh, we provide a more detailed evaluation of the proposed model using the rock curve and the area under the curve and the confusion matrix. The rock curves on the left show that the combining model achieves an AUC of 0.96, which is very close to BERT and clearly higher than random forest, demonstrating excellent discrimination between two classes. The confusion matrix on the right highlights another important advantage. The combination model produces only 2,224 false negatives compared with 2,669 for BERT and 4,003 for random forest. This represents the 44.5% reduction compared with random forest. In automatic content moderation, reducing false negatives, which is critical because it means fewer hate speech, mess, and remark. The last slide presentation is the performance and quality tests. Finally, this slide presents the performance and quality evaluation of the proposed web prototype. On the left, the Gmeter load test show that the system maintaining a 0% error rate with up 300 concurrent users, demonstrating stable operation under moderate workloads. Errors started to appear at 400 concurrent users, reaching approximately 51% at 600 users, which identifies the scalability limit on the current development. On the right, the Lighthouse assignment shows perfect score of 100% out of 100% in performance, accessibility, best practice, and zero. Overall, these results indicate that the application provides excellent web quality while maintaining reliability performance under typical conclusions. And go ahead with the last slide with the conclusion and future work. First, we are the main conclusion. First, the proposed multi-stage pipeline combining BERT and random forest and Gemini Flash, achieving accuracy of approximately 96%, demonstrating the effectiveness of the hybrid approach. In addition, the model reduces false negatives by 44.5% compared to random forest alone, improving the detection of harmful content. A key contribution of this work is the integration of Gemini Flash for gender-specific validation, enable the system to determine whether hate speech is explicitly directed toward women. Furthermore, the developed web prototype demonstrated the feasibility of developing the proposed approach in real-time content moderation. Our results show that a multiple-stage architecture improves the contextual understanding of gender-based hate speech. In future work, we plan to incorporate multilingual models such as MBERT and XLMR to reduce noise, fine-tune transformer models on gender-specific integrate emotion analysis to better capture the effective context message, and evaluate the system on higher traffic platforms with real users. Thank you for your attention. Tell me if can I help you something.
Thank you very much, Walter. Thank you very much for your clear presentation. I would ask to other people in the room if there are any questions or comments. Just a small question for you, Walter. Is this, as I understood, you are translating all the sentence to English, right?
Yes, it's too necessary.
Yeah. Is this hate speech sensitive to language or in another way? For example, a Spanish sentence, a hate Spanish sentence, when translated to English, will be the same, or can you lose something on the translation?
Um, as told you in this presentation, we use some translator to understand multi-language because the most data sets for training the model were in English, not in Spanish or other languages. So we use a translator online to achieve the better results of the training model.
Yes, I understood that. It was just a question if the language is important here. Yeah, but thank you for your explanation. So,
Thank you
thank you,
too.
Walter. We are moving to our next speaker. I
Okay.
think, thank you. I
Okay,
think,
thank you so much. Thank you so much. Bye-bye.
bye. So, I think Paul Batista is here to do the next presentation, right? Paul, can you turn on your camera and your sound? Maybe Paul is having. Paulo, enter the room again. Let's check if he's able to solve the problems. Hello, Paulo. Paulo, can you hear us? Your microphone is muted. Okay. Paulo has a challenge. Let's wait a little bit. We also have two more speakers. One speaker from Morocco. I'm, I think I cannot say the name correctly. Benny Mogo, Aurel Davi, Chocopono, and Ali Idri. Is any of these authors from Morocco here? Always. Yeah. This is a virtual session. And then the first one. The first one already presented?
Oh, okay. Was very fast.
No, it was on time.
Okay.
It was between 9:30 to 9:50. It was a nice presentation by Walter Fortes. Let's see, we have this broadcast on YouTube and you can check the video later if you want to. We are facing problems from the next speaker. Let's check if he's able to enter the room. So I think that's Fernanda Lima. It's also
Are you hearing me?
yes.
Okay, I need to change for my laptop. I don't know what happens with my main computer.
Okay, yeah, Paulo, are you able to share your presentation?
Yeah, give me 1 second. I'm so sorry. I need to understand why it's not working in the main computer, because I have tested and it is okay. But now it's not. Presentation is here. Are you seeing my presentation?
Yes. Not yet. Yes. Perfect now, Paulo.
Now it's perfect.
Yes.
Okay, I can start.
Yes, please. The floor is yours.
Thank you. I'm sorry for this short delay. Problems with the connection. I'm not sure why. Good morning, I'm Paul Batista. I'm presenting this work, When Do Electricity Price Forecasts Create Operational Value? This work is like a exploratory study that aims to identify the conditions under which case the price forecast can create value in industrial operational management. And the paper tried to evaluate the forecast as a decision signal, not as a typical forecast problem, because the question is whether this signal improves fixed plan of prices comparison against an alternative, which is a dynamic tariff of electricity prices. Okay. Our research questions are two. First one, which is about how the forecast behaves, the forecast model, how close are be able to predict hourly prices from the Iberian market, okay, the gross hourly electricity prices, and we assess these with the typical measures such as the mean absolute error and the root mean square error and so on. And the second research question, maybe the most focus on this work, is how the forecast can inform the policy to reduce the costs relative to a business as usual scenario, which is the fixed tariff, the fixed prices of electricity prices. And we assess this second research question by analyzing the tariff ordering, the proxy cost gains, and the risk of underperformance of this model. The motivation is mostly that forecast quality, if it is better or less accurate, and how it is combined with the business value for different measures and evaluations. Putting our problem in a more detailed way, we are focused on this decision layer, not in the forecast, the typical forecast layer of the electricity price forecast problem, and not in the value layer. How this is really value in a real world layer. We are in this intermediate layer, which is how to create value or information for a decision layer to decide if we should include some signals, some information of electricity prices on this more broadened problem of operational, of industrial operational production plan. Okay. What we do, we try to study this using a fixed production plan. We try to isolate the tariff value, the different policies, business as usual, which is the fixed tariff, and our alternative policy, which is a dynamic tariff indexed to the gross market. For that, we fixed the production plan, which is, we assume, which is the same in all our scenarios. And what are these scenarios? We evaluate our model in these three type of scenarios: low volatility, average volatility, and high volatility of prices. Okay, we try to do that by a statistical analysis, try to identify these three levels of volatility in the market, in the electricity market prices. And we get 5 samples for each one of the scenarios to do some statistical and some evaluation analysis. Our forecast, starting for our forecast model and how it works. Our model is basically to use a conservative design. Okay, we start from the price history. We model persistence 24 hours lag. Then we get the residuals from this persistent lag model, and and apply a machine learning model to predict the residuals and to predict these changes. Moreover, as we have a 1 week prediction horizon, we apply a shrinkage to consider this machine learning model on our model, and we finally produce these 168 forecast step ahead predictions. Okay, and here we have our shrinkage factors. We apply different shrinkage factors. How the machine learning contributes for our final model in each forecast horizon bucket. Okay. Then, as I say, we use a machine learning model only to predict the residuals, and we only use this information to correct our persistent lag 24 hours. And in this machine learning model, we have features such as the lags from the previous 6 and 12 hours, 24 hours rolling mean, and so on. We have some proxies for production, like renewable production, based on meteorological variables. Some proxies for demand, based on in meteorological information, and some population, and so on. Then what we define, we try to get, I'm sorry, we try to get the ordering of tariffs, okay, to understand how this model can be useful as a signal for our decision process. This evaluation, the evaluation procedure, as I say, is based on the forecast validity, on this tariff ordering, and then on more policy-related values, namely the gains, the average gains, and the risks. We try to quantify the risks in each our scenarios. Okay. And starting with results. First, this forecast model, we see that our forecast model is from the point prediction is better as expected in the low volatility, and is not so good at the high volatility weeks, which is expected comparison. But it surpasses our benchmark, our lag 24 persistent model in all regimes, but to another benchmark similar to our horizon of prediction, the 1 week prediction. It only is better than in average to the average volatility weeks. From the point of view of the tariff ordering, which is where our model is clear advantages for its simplicity, it provides a good alignment between our predictions, or the ordering of our predictions, and the real order of the prices in the market. Okay, with a high correlation, like near 75%, when in the different volatility scenarios. Okay, for the 5 samples that we get. The precision, which is how the ordering at the 24 lag or the 6 lag is exactly the same between the real prices and our prediction, shows that show a relatively nice alignment between them. And from the costs or the policy evaluation, we try to use this gain approach, and we see that in general or in average, the mean weekly gains are positive in all regimes. The policy, our tariff, dynamic tariff, is cheaper than the business as usual in 60%, 80% of the scenarios from low to high volatility. And the largest reversal, which is not which is our bad scenario, of course, in the low volatility weeks, okay, where the cost exceeds our business as usual scenario. As we see here in a more general overview, across the 15 weeks of our samples, 11 scenarios are cheaper, and 4 are worst cases, which can provide a conditional conclusion is that our forecast informed tariff can create savings, while downside some cases remain possible to be worse. Okay. From a cost perspective, to complement the previous one, we see that these savings they are not conditional to zero risk. In fact, they have some underperformance risk, which is greater, for example, for low, which can be 40%, but for average or high scenarios, it is relative lower. Okay, in the low scenarios, the problem is that the model struggles to be very accurate in the prices and in the order, okay, of our predictions. Then, as a conclusion, our main contribution is that this regime-aware evolution can be valuable under some bundled industrial flexibility. The framework tried to connect this forecast diagnostic, this tariff ordering, with the realized value to inform the industrial planners how it can be useful to include these as part of a more broadened decision support system. It's only to understand if this simple signal on the prices can be useful or not. And this shows that is conditional a good way. The operational value appears mainly from this tariff ordering, and this is sufficiently to improve our business as usual solution, the typical fixed tariff plan. But we should be aware of these risks and these problems related with the probability of getting worst cases, okay, which are not zero. And we show this. I'm sorry, I think to show the last one related with our future work. We try to revise and tune our machine learning model. We should revise and then the bucket specific shrinkage parameters, and we span from fixed plan tariffs to constrain our production resequencing. Okay, try to analyze how this behaves in a more broadened decision support system. And I think is everything. Thank you.
Thank you, Paul, for your presentation. I think the presentation was clear, the slides were clear. I don't know if anyone has questions or comments regarding this paper. Yes, please.
It's not really a question, it's more a curiosity. Good morning, Paulo Batista. João Mendes from IPB, Bragança. And I just have a curiosity of your work because you are using the prices of the electricity. That data set is based on Portugal or is from other countries?
It's from Portugal, yes. Is developed with a company from microprocessor from Porto, from near Porto, which develops decision support systems for industrial companies to help monitoring and reducing costs in the production plan. Okay, and we are exploring how we can add these price signals to a more broadened optimization mechanism. Okay, we are aware that we can focus in the typical electricity price forecast. The problem is that is a big challenge, and to get a really good and accurate model takes time and is expensive and so on. And these exploratory studies only to try to understand if even a weaker forecaster can provide some value. Okay, is our main contribution. But yes, it was based in Portugal in the Iberian prices. Okay, in OMIE gross prices for Portugal, and even the data from the production is anonymized and so on, but is a real
Data. Just one curiosity, like the data is distributed like in a space of minutes, hours, or you have like the price for
hours.
the hours?
Hours. The price from the gross electricity markets until I think 6 months or so on was provided at hours, and we start when we start this project, we only have these hourly prices. Okay. Now OMIE is providing I think minutes or so on prices statistics from the market, but the model was started before that.
In hours, okay, because the knowledge that I have, I think the measure, at least the measures or the balance, at least in our houses, I don't know if the enterprises is the same thing, but in our houses, the balance is calculated in intervals of 15 minutes. So you have from 15 minutes, you can have a bigger save in the end of the month because you can calculate that balance in between.
Exactly. Yeah. Now the problem is that the as I say, the prices only start to be provided in quarters at 6 months ago, I think.
Okay, perfect. Thank you once again, Paulo. Very nice presentation.
Thank you. I'm sorry for my English is not so so clear.
So if we don't have any more questions, I will say thank you to Paulo again. Thank you, Paulo. I have just a comment. You have in slide 6, you have units on the first one, which is the percentage, but please review the graphics because we don't have units in the I-axis on slide 6. So, but maybe if you can change it, it's good to make it more readable, and you are sharing the slides. It's just a very small comment.
No, it's okay.
So,
thank you.
Thank you for being here, Paulo, and to being able to share your screen. So we are going to the next speaker, Aurel Davi, I think from Morocco.
Yes, exactly. Can you hear me?
Yes.
Can you see my presentation?
Yes, you already seen your screen. but not yet in full screen. Yeah, if you can.
And now?
That's the same problem.
Is it in full screen now?
Yes, it's good enough. It's good enough. You can start your presentation.
Okay, okay, okay. Okay, no, great. So, good morning, everyone. My name is David Chukwankwe, and I'm PhD student at Maurice Polytechnic University from Morocco and École Polytechnique Fédérale in Switzerland. And today I will present our work entitled Enhancing the Trustworthiness of Deep Ensemble via Explainability in Medical Imaging. And this work was conducted with my supervisor, Prof. Ali Idri, and it focused on an important challenge in medical AI, which is how to ensure trustworthiness of deep learning model. And in our settings, we focus on deep ensemble method, which is one of the state-of-the-art uncertainty estimation method. So why trust matter in medical imaging? And general in healthcare applications. In this setting, we can say that high accuracy alone is not enough for clinical adoption. And when we are developing deep learning model or AI models, the end goal is an end deployment in a clinical settings. So a model may achieve good classification performance, but clinicians still need to know two important questions. And the first one concerns the model reliability, which means can the model tell us when it is uncertain, especially for use or difficult case? And that is in general handled using uncertainty configuration methods. And the second side is the model explainable, and which means can the model show whether its decision is based on meaningful clinical features or characteristics such as lesion area rather than irrelevant background pattern. And this is why trust softness requires the both sides, alternative configuration and explainability. And in subsettings, if you want to push it further, we can also integrate aspects like fairness to be sure that model is fair against any demographic attribute. But however, these two aspects are often studied separately. And in our work, we argue that they should be considered together, and especially in high-tech domain like cancer diagnosis or screening. So, deep ensemble are widely recognized as one of the most effective approach for uncertainty quantification compared to methods which are well established like Bayesian method like variational inference or multi-cause dropout. But one thing is that they are pretty hard to explain. And when we talk about deep ensembles, it's a quite simple uncertainty quantification method where we train several models independently and combine their prediction, and the variability between the ensemble member give us a useful information about the model uncertainty. But existing explainability approach for ensemble model usually aggregate the activation map of individual model. And for example, they use a kind of simple average of the explainability map or weight the map with the validation performance of the different model. But all this strategy is a kind of global level aggregation, and that introduces two limitations. The first one is the fact that it's not sample specific, because a model can have a global average performance but still fail on some edge case or some individual patients. And the second one is that most of the existing explainability method for the ensemble settings is not conditioned on the ensemble decision, because they usually use the prediction of the each member of the ensemble to extract just the explainability math without relying on the full ensemble decision. And we know that there can be some contradiction between some ensemble members and the full ensemble decision, and that can introduce some noise in the final explanation. So the key question of our work is how can we generate explanation that reflect the actual decision of the deep ensemble while adapting to each individual sample? And that leads us to propose two a framework that we call ECAM and SECAM, which rely on the explainability method which is already developed for single deep learning models and aggregate them using a weight schemes and a selective schemes. So when we come to the first one, which is called ensemble condition class activation map, the idea is to generate a score cam. In our setting, we choose to use the score cam uh, uh, gradient activation method, the score cam explainability method, but it can be extended to any activation map method that we use for explainability. So for each member, but all these maps are conditioned on the final prediction of the ensemble. And this allows to ensure that the explanation align with the ensemble decision and not only with the individual model decision. And now, instead of according the same importance to each map from each model, we use the uncertainty of each single model to weight the explainability map. And this allows us to have a final explainability map which take account the uncertainty of each models to have a more I can say trustworthy explainability compared to simple naive aggregations. And the second aggregate, which we call selective ensemble class activation map, use a kind of different settings where we first selection the model which have a decision which is aligned with the ensemble decisions, and after use a uh, an, an evaluation metric for the quality of the explainability map generated by each of these models, and the one with the best evaluation metric are choose and we display its map. And these rely on the average the system metric, which combine three metric which is used to evaluate explainability map, notably the coherency, which evaluate the relation the covariance between the the image explainability map and the explainability map, which is generated based on the explainability map, which is generated. So it's kind of step correlation where we have the first part where we use the explainability map of the image, and after apply a second part on this explainability map to see if the same information is written in the explanation map. And the second one is the complexity, which is defined as the minimum part of I mean kind of the size of the region which is identified by the map as explanations, and the average drop is just the drop in terms of confidence of the model when we use the explainability map as uh, input for the models. So for our experimental setting, we choose to make the validation on the breast ultrasound data set, which have a size of 780, and which come with the ground truth mask, which we can use to make the evaluation of the quality of the explanation, which is uh, derived by the different method. And architecture, we go on the ResNet 50 because it's widely used in the medical imaging setting, especially for image modality like mammography, ultrasound, and so on. And we choose an ensemble with 10 members with a custom classification head. And as evaluation, we quickly evaluate the classification performance of the model and also the uncertainty quality. And notably, we use the predictive entropy, which is the widely used measure of certainty in the uncertainty literature, and and compare the alignment with the explanation that we have with the qualitative mask. And that the goal is not fully optimizing the accuracy of the model, but more focused on the explanation side. And first, as quick quantitative results, we as accuracy, the model, the deep ensemble show an accuracy of 88%, and all the metrics were around 88%, which is good as baseline and close to what the state of the art on this data set in the literature show. And when we go to the uncertainty measure analysis, we can see that there are kind of difference in terms of distribution from correct classified sample and incorrect classified sample. And that means that the uncertainty measure can be used to flag uncertain case for secondary review in the setting of selective prediction. And when we come to the explanation map analysis, we try to probe the explanation map in the different conditions to also see the setting where it work well, and also the failure mode. And what we mark here on the left, we have the case where the model correctly classified the image and accurately localized the region of interest. And in this example, we can remark that the ACAM and SECAM produce artificial map data well aligned with the ground truth mask. And compared to the VCAM baseline, where they use the validation map, validation performance of each uh, individual model to weight the different map, we can remark that it have also kind of good localization performance, but our method propose a more focused and semantical meaningful explanation. And that can suggest that conditioning the map on the ensemble prediction and using a kind of uncertainty aware selective strategy can help to generate more reliable explanation. And on the right side, we try to analyze the failure modes. And there are some examples here which show correct classification, but incorrect localizations. And this means that the model are able to predict the right label, but focus on region that does not correspond to the annotated lesion. And this is important because it shows that this good classification performance does not always imply meaningful reasoning. And the second thing that it highlights is that maybe the model are able to identify other meaningful or clinical useful feature which is not maybe not take account by the original ground truth mask. And in this settings, a clinician with his expertise can further analyze this kind of map and see if there is no other emerging clinical characteristic which can characterize the pathology which is studied, or if it's not the emergence of new clinical features. And in the green frame, we have the settings where the model make misclassification, but with correct localization. In this case, the model identify the relevant anatomical region, but still assign the wrong label. And this suggests that the error may come from the difficulty in discriminating between benign and malignant features rather than from poor localization. And in the clinical context, an experienced clinician can easily rely on it and, for example, be able to take the accurate decision of the patient even without taking care of the classification that is done by the model. And uh, conclude, in this study, we propose two explainability methods for deep ensemble in medical imaging, notably ECAM and SECAM. And ECAM provide an uncertainty awareness ensemble explanation by weighting individual CAM according to the model confidence. And the SECAM method provide a selective explanation by choosing the most relevant ensemble member whose prediction agree with the final ensemble decision. And our results on the breast ultrasound diagnosis dataset show that this method can produce clinical meaningful explanation map and reveal important old failure. And the main message of this work is that trustworthiness in medical AI should not rely only on accuracy, and it should combine predictive performance, uncertainty quantification, and explainability. And as future work, we plan to further evaluate ECAM and SECAM on other medical imaging outside the breast cancer, such as histopathology imaging, mammography, cytology, and CT imaging. And we also want to study the uncertainty in the explanation themselves, because in clinical practice, I deeply think that it's not enough to know whether the model is uncertain about the prediction. We should also know whether the explanation which is produced is reliable. And finally, I would like to thank my supervisor, Prof. Ali Idri, the Exafton PhD program which fund my PhD thesis work, and all the faculty members of the Faculty of Medical Science for their support. Thank you very much for your attention.
Thank you very much, Aurel. Thank you. Are you finishing your PhD? Are you in the middle? How is your?
Right now, I'm in the third year. I will finish next year.
Okay, good. And thank you for your presentation, for showing both the good things you already achieved and also the failures. And it was a very nice presentation. I don't know if there are any questions. Auri?
I can have one question.
Yes, please.
So thank you very much, Aurel. Sorry by the spelling, okay? João Mendes from IPB, Bragança, Portugal.
Okay.
I already tried to apply something like this, not to medical images, but more with agriculture images. I developed also some work with explainable AI, but in this part of the images, we are always, or at least at the point where I applied, that I ended like 2 years ago, we are always a little stuck in the results, because basically what we have is heat maps, and I think you have the same results as I have. So basically the last evaluation always depends on the person that is checking the results, and we don't have quantitative data to prove that. So basically we only have qualitative data. Do you also feel this difficulty? There is you don't have numbers to sustain the model itself. You need to trust in the qualitative data.
Yeah, thank you for highlighting these questions, and I agree that it's a great pain point in the explainable AI side, mainly when we are in the deep learning, where we rely on the explainability map, which is activation map, and most of study rely on qualitative analysis. But the interesting part is that recently there are some quantitative evaluation metric which is introduced, and that people start using to evaluate quantitatively the quality of this map. But the thing is, to make this kind of evaluation, you always need to have a kind of ground truth annotations. And that's the thing about, there are measures like RDCC metric data used to select the one on the model on which we're gonna rely for the SECAM explainability method that I propose for the deep ensemble. And there are these methods which emerge now in the fields that can be fully used to make quantitative evaluation, to compare method and to evaluate the models. So I think that the field is progressing, but many people still relying on the qualitative evaluations, and maybe for that either you need expert domain to fully validate the model on very large sample size data set, or either try to shift in terms of evaluation method and start integrating the new quantitative evaluation metric.
Thank you very much, Ariel, for your answer. It's very clear.
Thank you.
So, thank you for our presentation, Aurel.
Thank you.
We are ending this session now. We have a paper on the schedule, but it was tagged with a different color, so I think there is a problem with this author. So thank you for the previous speakers too, and please continue to attend the sessions till the end of this morning.
Right.
Thank you very much to all.
Yeah.
Disconnect.